Imagine you've got an egg that's Earth-sized. Don't worry, it's just a fun analogy. The crust would be incredibly thin, only 20 times thinner than the shell in relation to its diameter. Now picture holding that delicate giant. Even slight pressure could cause major cracks. Surprisingly, our planet isn't much different. Research by American scientists in 2016 found that beneath the ocean's surface, the crust is getting thinner at a rate of about 1.7 kilometers or 1.06 miles every year. But why is this happening and how does it affect us? Let's dive deeper. No need to break out the spaceship blueprints just yet. Earth's geological changes happen over millions, not minutes or hours. This thinning crust process actually started around 170 million years ago when all our modern continents were part of a single supercontinent called Pangaea. Over time, it broke apart into separate landmasses due to the slow movement of the lithosphere plates. But what's driving these massive shifts in Earth's surface? Let's uncover the forces behind this ongoing change. To crack this mystery, scientists have been studying the Earth's outer layer for over 2.5 billion years, taking 234 measurements of crust thickness across different geological eras. But to really get a handle on it, we need to go even deeper, literally. Beneath our solid crust lies a massive, hot layer of rock called the mantle. It's not oozing like molten lava, but rather a slow-moving sea of solid rock that makes up about half our planet's depth and an astonishing 80% of its total volume. This hidden world is where some of Earth's most powerful processes unfold. Let's dive in and explore. Imagine a gooey praline coating. That's basically what the Earth's mantle is like. It wraps snugly around our planet's core and stays scorching hot, carrying with it heat left over from its birth 4.5 billion years ago in a molten magma sea. Since then, the mantle has been slowly on the move, but not because of some superpower. It's due to thermal convection. You might have seen this same process happen in your morning coffee, where the liquid near the surface cools and sinks as it gets hotter closer to the brew. Same thing here, the rocks near the surface grow cooler and heavier, so they slowly start their journey downward into the depths of our planet. But here's the kicker: despite being solid, our mantle rocks can actually flow like a slow-moving liquid. So, near the scorching hot core, the rocks get lighter and hotter. They're like rising stars. Meanwhile, those closer to the surface grow cooler and heavier, sinking down into the depths. Now you might be thinking, wait, solids don't move like that under gravity. And you're right, but here's an easy way to understand it. Imagine a jar packed tight with balls. Tilt the jar just enough, and those balls will start sliding out of their spots and moving to new ones. That's basically what's happening in our Earth's mantle. It's like one giant, slow-moving pack of balls, responding to temperature changes. Think of the mantle as an enormous layer of packed balls. They're solid, but when you tilt the jar, they can slowly shift and move along. Just like in your jar, Earth's mantle balls are always on the move, but at a snail's pace. This slow motion is what we call convection, and it plays a massive role in how our planet cools down. By moving heat from the core towards space, it helps keep our climate just right. Not too hot, not too cold, perfect for life to thrive. But convection does more than just regulate our climate. It's also the force behind the Earth's geological activity. As the mantle balls move, they drive the tectonic plates that make up our crust to shift and change over time. This has given us some incredible gifts: a powerful magnetic field that shields our atmosphere from harm, and a thin but sturdy crust formed by the lighter rocks rising from deep within our planet's core. Although much of the original crust is gone, convection played a key role in shaping what we see today. Continents rising up over millions and billions of years to form the diverse landscapes we know and love. Now let's dive into the fascinating world of Earth's crust. It's not one size fits all. We've got our thick and mighty continents, with crust reaching up to 80 kilometers beneath mountain ranges. And then we have the oceanic crust, which in some areas is a whopping 10 times thinner. Scientists are really interested in this thinning process because it happens at fault lines where hot rocks from deep within the Earth make their way to the surface. And here's the cool part: the thickness of our oceanic crust depends directly on how hot the mantle substance beneath it gets. It's like a never-ending geological balancing act. Here's the things: when magma rises to the surface and cools down, it solidifies into our oceanic crust, and get this, the thicker the layer becomes, the hotter that initial magma was. Now let's talk about some seriously cool research findings. Scientists discovered not one but two amazing things. First, the Earth is producing much less magma now than it did back in the good old dinosaur days. And second, due to a process called convection, our mantle is cooling down way faster than you'd think. So, let's put on our time machine and go back 2.5 billion years. That's when the mantle cooled at an incredibly steady rate of around 6 to 11 degrees Celsius every 100 million years. But here's where things get really interesting. About 170 million years ago, something big happened, war, and it drastically changed how our mantle cools down. Ever since then, the rate has skyrocketed to an astonishing 68 degrees Fahrenheit or 20 degrees Celsius every 100 million years. Now, you'd think that as time passed and the Earth aged, its mantle would simply continue cooling at a slower pace. But nope, scientists were blown away by this new speed, especially considering it's been influenced by the leftover heat from our planet's formation and radioactive elements over billions of years. As geophysicist Van Avendonk from the University of Texas puts it, Earth is actually cooling faster than ever before in its entire history. So remember, this super fast cooling isn't something you'd expect to see in a warming climate. It's quite unique. So, let's dive back in time to the middle of the Jurassic period, around 170 million years ago. What triggered this massive change in our planet's cooling rate? It all starts with Pangaea, our supercontinent that began breaking apart into separate continents. This enormous shift involved a huge rearrangement of lithosphere plates, basically reorganizing the Earth's crust. As these continents started moving away from each other, something cool happened, or rather, something got cooler. The deeper mantle layers were now exposed to air and water, which sped up their cooling process. Scientists found that beneath the Pacific Ocean, the mantle dropped by about 5.4 degrees Fahrenheit or 13 degrees Celsius over 100 million years. But here's where it gets even more dramatic under the Indian and Atlantic Oceans. The temperature plummeted an astonishing 98.6 degrees Fahrenheit or 37 degrees Celsius during the same time frame. Now that we've cracked open this cooling mystery, let's focus on why Pangaea first split apart. Think distance. It played a huge role. As continents moved further away from each other, the mantle beneath them cooled down at different rates. This cooling process also affected the oceanic crust, causing it to solidify in layers that were thinner than before. But what triggered this massive continental drift? Stay tuned as we explore more clues about the breakup of Pangaea and how our planet's history continues to unfold. Here's what researchers have pieced together: a massive release of stored heat beneath Pangaea triggered its breakup, causing the supercontinent to fragment over millions of years. But let's zoom out. This ancient event can help us understand our planet's ever-changing landscape and how it shapes our world today. Now, you might be wondering if these geological processes could impact us in the future. While they won't pose an immediate threat, the Earth's core will indeed play a part in its long-term evolution. So buckle up as we journey through time, exploring what our planet might look like millions of years from now. Get ready to fast forward your way through time. In about 1 to 2.3 billion years, our planet's mantle is expected to finally cool down completely, marking a significant shift in Earth's history. But what does this mean? As the mantle cools, the magnetic field that protects us from harmful solar radiation will start to fade away. Take Mars as an example. After a devastating impact, the red planet lost its global magnetic shield and exposed itself to harsh solar winds. We can use this as a haunting prediction for our own planet's future, sparking questions: what would life on Earth be like without that vital protection? Let's dive into what could happen next. Here's the deal. Our planet's magnetic field is a real powerhouse for its size. It looks like a majestic whale when viewed from space, with the solar wind flowing smoothly around it. But what happens if this protective shield starts to fade away? If we lose it completely or just see it weaken significantly, major consequences will hit us hard. The ozone layer would collapse, leaving our planet exposed and vulnerable to harsh UV radiation. And that's not all. Weakened magnetic field means compasses go haywire, navigation equipment fails, and humans face a surge in skin diseases due to excessive UV exposure. The effects of losing our magnetic shield are nothing short of alarming. Now let's talk about what happens next. As our core cools down, tectonic processes come to a grinding halt, and volcanic activity screeches to zero. You might wonder, how does all this impact life on Earth? Well, it just so happens that the movement of those tectonic plates helps us avoid a major problem known as the greenhouse effect. When organisms pass on, they release carbon dioxide into our atmosphere. If it's not absorbed by the planet, we're looking at a serious buildup of this gas. Trust me, you don't want that to happen. Fast forwarding back to our present-day Earth, you'll notice that the thinning crust isn't just a far-off scenario. It's actually happening right now, and it can lead to some major eruptions. As magma starts rising from deep beneath our feet, weak spots in the crust become pathways for this molten lava to burst forth into our atmosphere. You're most likely to see these volcanic explosions in areas known as subduction zones, where tectonic plates collide and one gets swallowed up by another. These regions aren't just hotbeds for eruptions. They're also notorious for producing the most devastating earthquakes that pose a huge threat to human settlements. So, while our Earth might resemble an egg with its crust, the two scenarios, an actual egg cracking and our planet's crust thinning, are worlds apart. Contrary to popular imagination, a thinner crust doesn't mean we're at risk of a catastrophic split or spilling out molten rock. Thanks for watching.